All right, let's start today's lecture. So last time we were discussing this theorem, which shows that for sequences in real number system, being convergent and being Cauchy are equivalent statements, right? A Cauchy a sequence of real numbers is convergent if and only if it is Cauchy. Another way of expressing this fact is that the set of real numbers is complete. We will see this later when we start discussing metric spaces. We will see these concepts there, and so this will correspond to the fact that the set of real numbers is complete. Okay. All right, we proved this. Now let me start now with some definitions. Again, these are some definitions you are familiar with. Okay, so this is okay. A subset S of real numbers will be closed, is called closed if the set of if the set S prime of accumulation points of S is contained in S. In other words, if S prime is contained in S, then we say that S is closed. And a subset U of R is called open if R minus U is closed. So we have here two definitions. We define closed subset. So a set is closed if it contains its accumulation points, and it's called open if its complement is closed. Okay, these are the definitions. Okay. Let's see some examples. For example, the empty set is closed because what are the accumulation points of this set? You know, any finite set has no accumulation point. We know that. Therefore, accumulation set of the empty set is the empty set. Therefore, they are equal. Therefore, the derived set is contained in this set. Therefore, this is closed. Right? The set of real numbers, on the other hand, what is the set of what are the accumulation points of the real numbers? Well, any real number, if you take any point in the set of real numbers and any interval about it, this will contain infinitely many points, right, from real numbers. Therefore, any real number is an accumulation point. Therefore, they are equal, and therefore, this is closed. We know that if S is finite, if S is finite, then S prime, the set of derived, the set of accumulation points is empty, because no interval can contain infinitely many elements from S, and empty set is clearly a subset of S, so S is closed, right? So these sets are closed, but we know what? If a set is closed, then its complement is open. So since empty set is closed, since this is closed, its complement R, which is R minus the empty set, is open. Therefore, the set of real numbers is both closed and open. Okay. Similarly, R is open, closed, and thus uh, the empty set, which is R minus R, is open. So empty set is both closed and open. And we will see later that these are actually the only two subsets of R which are both open and closed. So let me write here as a remark. We will see later that R and Q, not Q, the empty set, are the only subsets of R which are both closed and open. Bunu genelde şöyle söyleriz. Which are both open and closed. Okay. And here we also saw that any finite set is closed. So if S is finite, then U, which is R minus S, is open. Okay. Because any finite set is closed, therefore U minus, R minus S is open. What else? We have seen that the set of integers, right? For integers, S prime was empty, therefore the derived set is contained in Z, and thus Z is closed, right? Z is closed. What else? We have seen also that the set of for the set of rational numbers, the derived set was what? Derived sets are dense in Q, right? Therefore, S prime is equal to R, right? If around any real number there are infinitely many rational numbers, therefore any real number is an accumulation of Q, and therefore S prime, in this case, S prime is not contained in Q, and thus Q is not closed. Okay. Is it open? Well, R minus Q, let's call this set P, the set of irrational numbers, right? numbers is also dense in Q, in R, and thus uh, the derived set of Q, the set of rational numbers, no, sorry, irrational numbers, is also equal to R, so that let me write it this way, so that uh, P prime is not contained in P, and thus as P prime is not closed, hence Q, which is R minus P, is not open. So Q was not closed, right? Is not closed and it is not open. Similarly, since Q is neither closed nor open, its complement Q P, which is the set of irrational numbers, is neither open nor closed. Okay. Uh, Similarly, P is neither. Okay, söyledim. Hence, both Q and P are neither closed nor open. Uh, Let me leave this as an exercise to you to show that the set of rational numbers is dense in R. Show that P is dense in R. Okay, the set of irrational numbers. This is very easy actually. The idea is very simple. You know that Q is dense, right, in R. So every interval contains at least one rational number. Take such a rational number, and to that rational number add square root of 2 divided by some big uh, natural number, so that R plus square root of 2 over n0 still lies inside this interval. Therefore, choosing this n0 big enough, we see that this interval will contain an irrational number, and therefore we see that every interval contains an irrational number. Therefore, the set of irrational numbers will be dense. Okay. Any questions so far? So here I want you to just write more details for this fact. Okay, what else? All right, here we have some facts and proposition. A subset B of R is open if and only if for every x in B, there is some delta positive such that the interval x minus delta, x plus delta is a subset of B. So this proposition tells us the following. This is a characterization for open sets. We defined open sets as the complements of closed sets, but this tells us something else. A set will be open if and only if every element of that set contains an interval which is contained inside B. Okay, so let's prove this. Let's start from this direction. So uh, assume that B is open. Okay, so I assume B is open. Now I have to prove the following. For any x, there is some delta, so that x minus delta, x plus delta lies inside B. Okay, so let x in B be given. All right. Then we know what? Well, then of course x is not in B. Okay, let me write this. Right, since x is in B, x is not in R minus B, where R minus B is closed, right? However, so let's call this set S. Let S be this set R minus B, right? Since B is open, R minus B is closed, and S is not here. Since S is closed, S prime, the set of accumulation points, is contained in S, and thus X cannot be an accumulation point of S, right? Because S is contained in S and X is not in S. All right. Well, in other words, X is not an accumulation point of S. Well, if X is not an accumulation point of S, then X is an isolated point of S. This means what? There is an interval about X, so that in that interval, in the deleted interval, there is no element from S. Hence, there is some delta positive, so that the deleted interval, which interval? This interval, x minus delta, x plus delta, minus delta, intersection of this with S is empty. Okay? This means what? This means the following. Hence, this deleted interval, evet haklısın. Sorry, we have to exclude x, minus x. This should be contained in since this has no intersection with S, this should be contained in R minus S, which is B, right? What about the point X? Well, X is already in B, right? We have chosen X from B. Where was it? Yeah, here, X is from B. So, not only this delete interval, but X is also in B. Finally, okay, let me write here. Finally, since X is already in B, we see that X minus delta, X plus delta, the whole interval lies inside B. And this proves the uh, first part of the proposition, right? So, okay, for the other direction, so this time, so this finishes the proof. Şöyle yazayım. This finishes the proof of the uh, this direction. If part. For this direction, let's see how we proceed. Now assume that there is some delta positive so that x minus delta, x plus delta lies inside B, right? Okay. All right. I have to prove that B is open, right? In other words, we have to prove that complement of B is closed. So we must show what? Let me write it here. We must show that S, which is R minus B, is closed. Okay. All right. But you see, let me draw you a picture. Here is X, and I have such an interval. This is contained in B. Okay. Okay, for every X, bir dakika, ne yapmak istiyoruz? Şöyle yazmam lazım. Okay, belki I have to be more careful. We assume that for every X there is such, we assume, okay, assume that for any X in B, there is some delta positive with X minus delta, X plus delta lies inside B. So we must show that B, complement of B is closed. Okay. So okay. To show that this set is closed, I have to prove that its derived set is contained in S prime. All right, so enough to prove that. Enough to prove that S prime is contained in S. All right. Now let X is in S prime, an accumulation point. Well, then we know that there is a sequence in S which converges to X, right? So there is a sequence xn in S so that the terms of the sequence are different and limit xn is equal to x, right? This is an equivalent statement for an accumulation point. So we have something like this. Here is x, and we have a sequence converging to this set. Okay. Okay, S is, we have to prove that S is closed. Okay, S is closed. I am a little bit confused. S is closed, so okay, so yes. Ama bir şey tarif etmedik. We didn't define what's an interior yet. Hı hı. Evet, öyle demem lazım da bir şekilde karıştırdım. Let me think about this for a while. Now we assume that there is some delta, so that this is inside B. We must show that R minus B is closed. So let S okay. Şuna gerek yok sanırım. Bir saniye. S is inside. Okay. So we assume that B is open. No. We assume that for any B we have this. I have to prove that S is closed. S is closed. So we choose some S prime. S, since it is in S prime, evet. Bir dakika, kafam karıştı da. Accumulation point'in tanımı, yani bir tane delta var değil mi? X minus delta, X plus delta, şöyle diyorsun. Then şöyle diyelim. X is here. Any interval about this contains some elements from S, right? Contains infinitely many elements from S. But şimdi şey nasıl olacak? Pardon ya, gerçekten kafam bir şekilde durdu, karıştı. Şimdi x eksi delta, x artı delta, şöyle diyeyim. Şimdi ne verildi bize? Her bir x için bu var. Ha, tamam. Bu ama şeye eşit. R minus S değil mi? Tamam. Okay. Yeah, we are done. Yeah. This is R minus S. But for being an accumulation point, then the interval x minus delta, x plus delta, since it is an accumulation point, must contain infinitely many elements. From S, right? Which is R minus B. But we know that this set is contained inside B completely, which is not, so this is a contradiction. Since this interval lies inside B. Okay, so we have the following. This set contains infinitely many elements from the complement of B, and it's also contained in B. That's a contradiction, right? So we are done. And peki niye contradiction? Ha, eğer şey olsaydı. Okay. Şöyle demem lazım. If x is in S, then the interval, right? Sorry, is in B. This is a contradiction. Hence, X should be inside R minus B, which is S. So we proved what? We proved that. So we proved the following: if X is in S prime, then X is in S. So uh, thus S prime is in S, and thus and therefore S is closed. So we are done. Okay. I am sorry for the confusion, but sometimes I just get confused. Do you have any questions? All right. Okay. So let's see some more examples of closed and open sets. For example, such an interval. Okay, let me say. An interval like this is open, right? Why is that? Uh, because you see, if you have an element from this, like this, so if X is in AB, then of course X is necessarily larger than A and less than B. So there is a positive distance from X to A and X to B. I can measure the two distances, take the minimum. So let delta to be the minimum of uh, X minus A and B minus X. Okay. Uh, and divide this by 2. So I measure the two distances, take the minimum, which in this case it is this interval, and divide it by 2. So delta is this. Clearly the interval, then clearly, sorry, X minus delta, X plus delta will be inside still AB. Therefore, I could find an interval about X so that this interval is contained in AB. Hence, AB is closed. Open. Okay. What about this set? Well, in this case, this is neither open nor closed, right? This is not closed. First of all, is not open. Is not open because no interval of the form A minus delta, A plus delta is contained in AB. right? You see, my interval is this, and if this is open, then about every element of this set, I should be able to find some delta interval that is contained in this subset. However, for any delta, the interval x minus delta, x plus delta, right, an interval like this will be never contained in AB, right? Not x, I should write A, because A minus delta is necessarily less than A, right? So you just go outside. Therefore, this interval is not contained here. Therefore, this is not open. It is not closed. Why is that? Because uh, R minus AB is what? This is just minus infinity A union, this time B infinity. This is not open either, because of the same reason. This time you play the same game for B, right? You see, your set is this. Here is A, here is B. This side is open, this side is closed. And you play the same game. This time you take this point, and you see that any interval about this, right? X minus, no, B plus delta, B minus delta. This won't be contained inside this set. Therefore, this set is not closed. Sorry, is not open, right? So, uh, uh, so this is not open. Uh, since it is not open, RB is not closed. Sorry, AB is not closed. Okay, so this interval is neither open nor closed. Okay, what about this one? This one, this one, and this one, these are all closed. Closed. Because their complements are all open, okay? So let me leave this as an exercise, this part. Okay. Okay. We will, so the next thing is not, is a theorem. So, okay. Let AK be a sequence of non-empty empty closed sets, subsets of R, such that A1 is bounded and all the rest lies in the previous one for each k. So A2 is inside A1, A3 is inside A2, and so on. Okay, so we have something like this: A1, A2, A3, and goes like this. The conclusion is this: then this intersection AK, so you intersect all of them, okay, is not empty. So if you have closed sets which are all non-empty, and if they are contained inside each other like this, okay, A1 contains A2, A2 so contains A3, and so on, then the common intersection is never empty. You may think that, this is trivial, right? I mean, these are all non-empty, and one is contained in the next one. So why, should the intersection be empty? But we will see that it is not easy to prove this, because there are some counter examples if you drop some of the assumptions, like being uh, non-empty, or being of course, if you drop the assumption being non-empty, the intersection will be closed, but the key fact is that these sets are closed. Before I prove this, I will give some examples, but I'll give these examples in the second hour. Okay. All right, let's give a break. After the break, I will continue, okay?